So we will deal now with the exercise 3 problem 2, and here you have written for shielding purpose at a frequency of 30 megahertz a plate of aluminium is used. So we have here first the frequency of operation, it's around about 30 megahertz, and in the case of aluminium we have a kappa Al, it's 3.65 10 to the power of 7, and it's the unit, it's 1 over ohm meter. This is the conductivity of copper. So the skin depth in Al 30 megahertz. So according to this equation we can write delta RL, it will be the square root of 2 over omega. Of course it's the circular frequency. Then of course we have here to insert kappa RL, and since aluminium has no magnetic properties, or the relative permittivity, no, the relative permeability of aluminium is 1, we have to insert here mu naught. So we can now insert the values here, and you will see first the 2 here, and we have here 2 pi, and here we have 30 10 to the power of 6 1 over second, so hertz here, and then we have here 3.65 10 to the power of 7 ohm over meter. They will come here, and we have mu naught, it's 4 pi 10 to the power of minus 7 volt seconds per ampere meter. Of course it's of advantage to, instead of using ohm here, we should use here volt over ampere, and then you see this will cancel, the volt, the seconds will cancel, the volt will cancel, and the ampere will cancel, and we will get the result in meter. So, and if you calculate the value, of course you just have to calculate the value here, and if you do it, RL will be then, I'll have a look here, and it will be 15 point, no, not very nice here, 15.2, and as a result you will get 10 to the power of minus 6 meter, or 15.2 micrometer. This will be the skin depth. And what does this mean, the skin depth? In principle, the skin depth describes how the electric field and the magnetic field of uh, of the plane wave decays into the conductor. So it will decay in a short distance, it will already decay. So and the next question here is, give it as a function of the frequency in megahertz. So you see here that the frequency, it will be always proportional 1 over the square root of the frequency. So I want to have in principle these form the skin depth of aluminium. Of course we see it will be somehow equal to a value, I call it for example x here, in micrometer, and of course due to the fact that it's proportional to 1 over the square root of the frequency, we can say, we can formulate it like this. This must be somehow proportional to the square root of the frequency in megahertz. So of course you see, if I insert now the frequency in megahertz here, the megahertz will cancel and we will get the value, for example, here we can use the 15.2 for 30 megahertz. So we can write, you see here, 15.2 micrometer will be equal to x micrometer divided by the square root of 30, because if I insert the frequency in megahertz, the frequency will cancel here, we will only have the 30, and here we can now cancel this, and you see now we will get x will be then 15.2 times the square root of 30. And if you calculate this value, then you will get this x, it will be 82.2. And from this we can now say, if I want to calculate the skin depth now as a function of the frequency, we can now use this formula here and can say the skin depth in RL in aluminium will then be equal to 82.2 micrometer divided by F divided in megahertz. So you don't have to always to insert all these complicated numbers. So you just use this expression now to calculate the skin depth in aluminium as a function of the frequency in megahertz. So are there some questions here?
It asks to give us a function of frequency. It just mean that we plug in the copper conductivity and the permeability, and then we work out a number, and then we leave the S as a variable, right? It just mean that.
Yeah, we just leave the frequency as a variable here. But you see, you must insert the frequency in megahertz. Only if you insert the frequency in megahertz, then the megahertz will cancel and then you get the right result. So you must account for the unit of the frequency, of course. So if we want to calculate it at 1 kilohertz, of course, then you must change the kilohertz into megahertz and so on. So perhaps I sketch this here. If I, for example, sketch the magnetic field, so in the lecture notes, perhaps I give you the figure. This is in principle figure 5.6 in the lecture notes. And there I showed what happens to the magnetic field on if it penetrates into the conductor. So this is the z coordinate, and for z greater than 0, though in this region we have a certain conductor. I sketch it here. Here we have kappa L, a certain conductivity, and now I draw in this region the magnetic field in the y direction as a function of the z coordinate to the magnetic field with reference to the magnetic field on the surface. And I'm only interested in the absolute value. The absolute value here. And then we will see that this decays. So we will have here a 1. So at the surface you have this value, and then it drops by an exponential function like this. And this is proportional to the exponential function of minus z over delta RL. So it will decay according to this exponential function into the material. So from this we can of course say, but we are only interested in the amplitude, so if I take the absolute value of the phasor, then we come to the amplitude. So we can say the amplitude of the magnetic field of Z will be equal to the amplitude h0 on the surface times the exponential function of minus Z over delta RL. So this describes how the magnetic field decays into the conductor, and also the electric field would decay into the conductor according to the same function. And now the question is, at which distance z from the surface the magnetic strength is attenuated by 80 dB. So you see it decays down here, and there will be a certain distance where we have a damping of 80 dB. And what does this mean? Now if I use the dB value, then I can say, if I use the dB value, then we must say that we have 20 log. If the dB scale is a log scale, and we have 20 log, and if I say I have a decay of 80 dB, so we must get a positive number, so we will have that this is y0 divided by y, the amplitude at a certain distance d. And this must be 80 according to our definition here. So this is in principle the dB scale now, and we will have now, if I insert this, of course, you see I can write this here, and then we will have 20 log, and I solve for this ratio here, then I have to insert the d here of the exponential function. Perhaps I write it like this is e to the power of minus plus d over delta RL, and this must be equal to 80. Or we can see that this is 20 times d over delta RL times log of e, where log I mean the logarithms with base 10, and this gives 80. So perhaps I delete here this picture. And then I can, of course, 20, this gives 4 in principle. Yeah, now we can say the distance with reference to delta RL must be 4 divided by the log of the natural logarithms of the log of e, and so we get for d it's delta RL times 4 divided by log of e. And of course we can insert the numbers now. We had at a 30 megahertz we have 15.2 micrometer times 4 divided by log of e, and I just will calculate in with log 1 over times 4 times 15.2, and we will get around about that the distance d must be round about 140 micrometer. So you see that already a very thin metal sheet of aluminium would result in a very high damping, and this is used for in the older radio receiver. Of course, there you will see that the radio receiver are shielded inside with a aluminium metal sheet, a very thin aluminium metal sheet.